Hi, my name is Jason Gross. I'm a professor at West Virginia University, and I'm happy to share a video abstract for our paper, Cooperative Localization for GNSS-Denied Subterranean Navigation, a UAV-UGV team approach. In this paper, we are looking at applications such as search and rescue in underground tunnels, mines, where environments are dirty, dusty, dark, and we want to leverage a heterogeneous approach where we have a ground robot with more capable sensing and computation and a drone that can provide eyes in the sky. In order to solve this, we take a multi-sensor fusion approach with different sensors that are capable in different environments, such as low light and also dusty. We formulate this as a cooperative localization where the ground robot is solving its own state using simultaneous localization and mapping, and it is also tracking the state of the UAV with some of its sensing, combining sensors on board of the drone to provide a robust localization system. So we have things like lidar, ranging radio. We also have inertial on both. We have stereo vision on the drone and a ranging radio between the two vehicles, as well as an altimeter on the drone. In addition to formulating the problem, we also solve it using two different popular nonlinear estimators. This problem is small enough that the batch-like nature of the factor graph is something that is feasible to be realized. So we wanted to compare and contrast these two state estimators, with the EKF being the more traditional approach and the factor graph being the more popular up-and-coming approach, showing the benefits and drawbacks of the two. In order to provide insight to the reader, we needed to have a truth state of the drone. So we tested at a motion capture facility here at West Virginia University, where we use Vicon cameras to track the position and attitude of both as an independent ground truth. One deviation from our past work that we've published at the Institute of Navigation conferences is that both the ground robot and the UAV are moving at the same time in these tests, meaning that the ground robot needs to have a solution of its localization in the environment using something like, in this case, simultaneous localization and mapping. So in the end, we were able to show a GPS-like localization of the drone with respect to a ground robot. And in the paper, you'll be able to read more details about some effectiveness of different sensor combinations and also some benefits and drawbacks in comparisons of the performance using two different popular nonlinear estimators. We also identify some future next steps of the work, including making the system overall more collaborative, where both vehicles benefit from this shared localization data. So thank you, and I hope you enjoy the paper.